Hello and welcome back to my channel, and today we are actually going to do Borel sets, but I want to touch on points of closure and we move on to the Borel set. Okay, so the last time we talked about an open set and we talked about a closed set. Okay, so before I move on to the points of closure, there was something I didn't say about the open set. The open set is actually the open set is a disjoint intersection or in the disjoint union of other open intervals. Okay, so it is the disjoint union of open intervals. Okay, open union. So you have so many open sets which you find its union to get an open set. So this actually makes us know that the union of open sets is also open. Okay, and when we did topology, anytime you're given a topological space X, okay, you find on say tau is this, then we know that first of all tau and phi are um, topologies, right? They are open sets. Sorry, they are open sets. So it's like anytime you have a space, okay, you have a space, the space itself is an open set, and also the empty set is also an open set. Okay, yeah. So okay, we have X and phi being open sets, and then the union and intersections, the union and intersection of open sets they are also open. Okay, so if you're talking about the real numbers, the set of real numbers as your topology here, like as a space, then the set of real numbers itself is open. Okay, and also you should have phi also open. Okay, so the empty set within the set of real numbers is open, and the set of real numbers itself is also an open set. Okay, then the union of open sets and the intersection, oh sorry, the union of open sets is also open. Are you okay? Yeah, so basically we have the set of real numbers being open and phi also being open. All right, so now let's move on to points of closure. If we know a closed set. Okay, so let's move on to points of closure. Now, if you have a closed set, a closed set contains all its points of closure. Okay, a closed set contains all its points of closure. So what then is a point of closure? Now, if I draw a set, let's say this is this interval. So this is an interval A and B. If a point here X is a point of closure, then what I'm saying is that with any open interval I can get with this X, any open interval like an interval which contains X, which could be a neighborhood of X, should contain another element of the set. Okay, it should contain another element of this set. So with this set, when I pick any point, right, in here, and I find any neighborhood of it which contains another element within the set, then that point is a point of closure. So it is easily seen that all the interior points over here are points of closures. All right, so all these points here are points of closure. Okay, yeah. So when I pick the boundaries, let's see, you can actually see that anytime you draw an open interval which contains B, there will be a portion which is found in the set. So the boundaries are also points of closure. So you can actually see that the definition of limit point is actually in conjunction with the definition of points of closure. Okay, yeah. So if we group all these points of closure, then you have a closed set. So closed sets contain all their points of closure. Okay, so if say A is contains all its points of closure, then it is denoted by this A bar, the closed set A bar. Okay, so this is the closed set you have here. It looks like the complement, but then we are talking about closed sets over here. Okay, yes, and we know that if a set is closed, then its complement should be open. Okay, yeah, so that one too, we have to know them. Okay, so these were some things I couldn't say in my previous videos, but I'm telling you here. And one thing you have to know about finite sets, I forgot to talk about that too. Finite sets, you see, we remember that if a set is said to be finite, then there exists a certain natural number and such that the set is equipotent to the sets 1 to that n. Okay, but that isn't only the definition. That I didn't add up a certain part of it, which is the set can also be empty. An empty set is also a finite set because you know the number of elements in there, which is empty. There is nothing in there, so you know it's the number of elements in it. So the empty set is also finite. It's finite. So I'm very sorry for not adding that over there, but then you should know that phi is also the set of empty the empty set is also a finite set. Okay, so now let's move on quickly to the Borel sets. Very quick. Borel sets. Okay. Borel sets. Borel sets. All right, so now I actually typed under my previous videos that when we were coming to Borel sets, we were going to need the understanding from open sets and closed sets. Okay, so now let's do that very quick. Now, a Borel set is said to be a subset of the set of the Borel-Sigma algebra. So say B is Borel, let's say this B is a Borel set, then it is a subset. It is a subset of the Borel-Sigma algebra. So it means we have to know what a Sigma algebra what Sigma algebra is. Okay, so let's define what a Sigma algebra is. So Sigma algebra is actually a collection of sets. Okay, it's a collection of sets. Collection of open and closed sets. Open and closed sets. Okay, so you have open sets and closed sets within this. Okay, yeah. So which satisfy these conditions. They satisfy these conditions. So one, it's like topology. All right, it's like a topology. You should have the empty set being a part of the Borel set. Sigma algebra set. Okay, so this is the Sigma algebra, and also you are saying that it contains both open and closed sets. And from topology, if you are defining a discrete topology, you know that it is the maximum topology you can get from a space. Okay, and you could see that with any open set within it, its complement is there, and we know that if the complement of any set is also is also open, then it means that that set itself is a closed set. Because if my complement is open, then I am closed, but at the same time it was open, okay, in the set of in the discrete topology. So in here too, if a set A is going to belong to this Sigma algebra, so this is my Sigma algebra, this kind of A tilde, this is my Sigma algebra, then its complement is also in A. So that's actually going to take care of the closed part of the whole thing. So you always have your phi always being there, and also if A is in this Borel the Sigma algebra. So this is the definition of a Sigma algebra. That's what we are talking about. Then its complement, if A is in there, which is an open set, its complement is also there, which makes its complement the set which is open closed at the same time. Are you getting it? Yeah. And the last one is that the union, the countable union. So it's like topology, the countable union of sets. Okay, a countable union of sets in this tilde A is also in A. Is tilde A. So these are the three basic things you have to know about the Sigma algebra. So we know that it's a collection of opened and closed sets. So it means that the Borel set is a collection of open and closed sets as well. But what is going to be peculiar about this Borel set? When you pick any set, okay, a set, and you want to call it a Borel set, then it means that with these collections you can have numerous collections of Sigma algebra. Okay, you can have so many Sigma algebra from a set. So say I have this set, a set maybe 2 to say 7. Okay, or let me take the raw line to explain it a bit better. So my real line starts from negative infinity to positive infinity. Now I want to have subsets of this real line, which is going to be a Borel set. Okay, so one thing I have to tell you is that any set which has this form is a Borel set. So let me define what the Borel set is. With all these collections you are going to pick, there can be numerous collections which are going to depict this behavior under the real line. Okay, there are numerous of them, like so many of them, which can depict this definition under here. But the Borel set deals with, it takes the least or the smallest of these collections. Okay, so if I have the Borel set, the Sigma algebra, and I am able to get so many Sigma algebra from a certain domain, the smallest of them, the smallest collection gives me the Borel set. The smallest collection I can get, that gives me the Borel set. Okay, yes. So when I come here, any set which looks like this is said to be a Borel set. So it means that examples, I can pick this as an example. 2, 7 is a Borel set. 3, 5 is a Borel set. Okay, so somebody might ask, we are saying a Borel set is formed by continuously taking the intersection and union of what sets, open and closed sets. So you repeatedly find unions of open sets and closed sets, and you are getting what a Borel set. You do that repeatedly. So once, and we know that it is a subset of this sigma algebra, which has this definition. Okay, yeah, but we said with this definition we pick the smallest of the collection, and that is our Borel set, right? Yeah, that's our Borel set. So now when we come here, somebody might compare these two and say, all right, this is smaller than that, but that is not what we are talking about. We are talking about the smallest collection of sets. It's a collection of subsets, okay? Collection of open sets and closed sets. All right, so you know that 2 to 7 is closed and open at the same time, but then it has infinitely many elements over here. There are infinitely many elements over here, and when I take 3 to 5 to as well, there are infinitely many elements over here. So since the number of elements are infinitely many, you can also have infinitely many subsets over here, and you can also find infinitely many subsets over here. So if I want the number of collections I'm having for this, there are infinitely many, and this one too has infinitely many subsets, possible subsets you can think of. Okay, yes. So since this one has infinitely many, and that also has infinitely many, there is no smallest of them. Like, they are all of the same magnitude. Like, they all have the same number of collections. All right, yes. So it then makes them all Borel sets, even though visually you can assume this one being a bigger set than that. It doesn't happen like that. They all have infinitely many elements, or infinitely many collections of opened and closed sets. So it makes both of them Borel sets. So anytime you're going to see any set which looks like this, it is a Borel set. Okay, so that's where I'm going to end with this video, and in our next video we are going to start with our Lebesgue measure, or the Lebesgue outer measure. So see you in the next video. If you like the content of the video, just drop a like and subscribe to the channel. Thank you.